Hello, everyone. I'm very delighted to give a talk in this prestigious workshop. I'll give a talk on planet formation in stellar clusters. And as you might already know, planet formation studies are really very rare. And planet formation studies which incorporate stellar cluster environments are even much more rarer. Well, that is not good because as the previous speakers hinted, that most stars form in stellar clusters, and around these forming stars, planet normally forms. And now, if these are really true, then the big question is, why are there few planets observed even in open stellar clusters where it is expected to have a favorable condition for planet formation? Now, one might think maybe this is due to observational difficulties, or is it that planets start forming in the disk after they escape the clusters? Or maybe in stellar clusters, conditions are not really good for planet formation. Well, indeed, few studies pointed to the fact that it's really very difficult to observe planets in stellar clusters, and this could be due to false positives, which can be related to stochastic trajectory of very many celestial bodies, or this could be due to maybe shallow dips in the light curves due to the super bright background from the stellar cluster. And it could also be due to incompleteness of survey. Well, the next big question is, what are the conditions in stellar clusters and what do they mean to planet formation? It is without big doubt that within stellar clusters, there exist flybys, and these flybys can cause truncation of disk, and it can also cause ejection of planets at the outskirts of the disk. Also, there exists photoevaporation from radiation of different typologies, and this can dissociate gas and therefore shortening its lifetime. And also, these radiations can sweep already formed atmosphere of gas giant planets. Well, also not to forget, within stellar clusters, there exists background heating, and this can really affect the disk profile of it can affect the disk profile, and that really has a lot of influence on planet formation. Well, now sometimes in sciences it's really good to isolate object of interest from non-object of interest for clarity reasons, but we need to remind ourselves that sometimes it's not always, especially for planet formation studies, since we agreed and the previous speakers have hinted that planets start forming from the disk. So it's really very important to include stellar cluster environment while modeling planet formation studies. Well, planet formation models, the major widely accepted planet formation models are the co-accretion models and the gravitational instability models. Since I'm a disciple of co-accretion model, I'll give a talk regarding co-accretion model. Well, in the co-accretion model, a bottom-top approach is followed, where the already existing planetary egg start accrete solid material from the disk, and this solid material are either aerodynamical coupled pebbles, which are millimeter to centimeter size particles, or the planetary embryo can already start to accrete the big guys, the planetesimals, which are the kilometer size particles. Well, the accretion of the solid material proceed until the critical mass is reached, called isolation mass. And at this isolation mass, a pressure bump is generated, and this pressure bump reverses the gas drag, and because of this, the solid materials or the dust are trapped at the exterior orbit of the planet. And if this critical mass is reached, when there is still gas in the disk, then the planetary embryo can eat gas. Well, also what is important in planet formation is that the protoplanet also perturb the disk, and because of this, it normally exchange angular momentum, and the exchange of angular momentum can translate into dragging the planets toward the host stars or away from the host stars, what we call migration. And this migration can be type 1 for the low mass planets, or it can be type 2 if the planet really grow very big and open a deep gap in the disk. Well, I'll now immediately discuss to you a few results from my master thesis, which was done under supervision of Bertrand Biss. Well, the work was really very simple. So what we did was we incorporated the background heating from stellar clusters, and we did that by expanding the disk model of Biss. And what we found was that really even a mere inclusion of the background heating from stellar clusters can really change things. Can really change the profile of the disk. For example, in this plot, we've got on the vertical axis, we have the aspect ratio, and on the horizontal axis, we have the distance from the host stars. So the different colors in this plot shows the disk profile from different cluster environment. Well, what one can see clearly here is that if you have a hot background from stellar clusters, it gives rise to highly flaring disk profile. For example, you can have a look at comparative look at this green curve, which shows background disk profile from cluster of 100 Kelvin, and the blue curve shows this profile around field stars. Well, now the big question is, what does this highly flaring aspect ratio means to planet formation? Well, if you remember very well, I already hinted that pebble isolation mass is really very powerful dichotomy between low mass planets and gas giant planets. So, and this pebble isolation mass scales cubically with the aspect ratio. So the higher the aspect ratio, the higher the pebble isolation mass. So the rule of the game is really very simple. Well, if you have high pebble isolation mass, you take longer time to accrete solids, and if the accretion rates of these solids are really very low, it means that you spend most of your time trying to reach this pebble isolation mass. So by the time you reach gas accretion, the gas in the disk might be already dispersed. And from this simple analysis, we can already see that it's really very difficult to form gas giant planets in stellar clusters. Well, this is really very simple analysis and does not really tell us a lot. So what we did was we expanded the parameter space by performing a simple planet population synthesis. Planet population synthesis is a very powerful tool which tells the strength and weaknesses of model by comparing the model. And it works in a very simple way. So the first thing is normally what's done is you randomize the initial condition of planet formation, and this can be derived from observational constraints, or if they don't exist, then you can use an attractive educated guesses, and the various combination of the initial condition of this important planet formation conditions generates population of planets. Now, once you generate the population of planets, you can compare the population of the planets to observation, not only to observation, but to the portion of observation which is well biased. Now, from this, you can tell whether a model is really doing well or bad in matching the observation. Well, this is exactly what we did, and we found that we got a mass distance distribution of the synthesized planets, and this plot on the left source simulation around field stars of background heating of 4 Kelvin. And here we saw simulation around stellar cluster with a background heating of 40 Kelvin, while here we saw simulation around stellar cluster of background heating of 100 Kelvin. Well, again, on the vertical axis, we have the mass in Earth masses, and here we've got the distance from the host stars in AU. Well, what we can see here is we see a lot of colored plots, and these colored plots shows for you that the synthesized planets and their corresponding metallicity environment from which they were simulated. What one can see here is that the higher the metallicity, the higher the rate of formation of gas giant planets, because you really have enough building block to reach the isolation mass, so you can start accreting gas early. Therefore, it will enhance the chance of gas giant planet formation. Also important to note here is as you move from field stars to stellar cluster environment with higher and higher background heating, you realize that it's really very difficult to form gas giant planets, with the higher cluster being even almost impossible. So what we did next was to perform very simple quantitative analysis where we categorized these planets into various forms, and the super Earths, Neptunian, hot Jupiter, warm Jupiter, and cold Jupiters. And what's really very important here is that we realized that in around field stars with very low background heating, let's say of 4 Kelvin, you realize that it is far much easier. I mean, the gas giant planets are the majority compared to the super Earth planets. This is not right, because observation tells us that you expect super Earths to be the majority compared to the gas giant planets. Now, what's really interesting is as you move to hotter background heating, you realize that the reverse is true. Now, you realize that it is far much easier to form super Earth planets compared to the gas giant planets. Well, so what we did next was to zoom into the region where we have gas giant planets that can be captured by the radial velocity field techniques. And what we did was we calculated the occurrence rate of planets in this regime, and we compared it to the gas giant fraction extracted from Johnson 2010. And this is what we got. We have on the vertical axis the frequency of giant planets, and on the horizontal axis the metallicity from which these planets were formed. And the gas giant fraction from the observation is denoted by the purple curve. And one can immediately see that if you have a hotter cluster environment like the blue guys, it comes close to what observation tells us. But if you have simulation, the simulation around is isolated field stars overfits what observation expects. So another important thing this graph tells us is that you realize that in all of our plots, there is disparity between what observation tells and the curve. I'm talking in terms of the shape, especially at the high metallicity, where at the high metallicity, you see our occurrence rate shows saturation effect. Well, we found that this saturation effect is related to initial starting position of the cores and migration. Well, we also lately realized that you can actually mimic this shape when you include the n-body paradigm. Well, from our simple quantitative analysis and our simple comparison to gas giant fraction, one can already conclude that maybe if you accrete solid onto planetary embryo at faster rate, especially for paradigms like pebble accretion, maybe you need hotter background like in stellar clusters if you really want to match the gas giant planets. Now I'll leave you the following remark that first of all, we model the background heating from stellar clusters, but we did not incorporate the impact of clusters on truncation of the disk, and also which consequently results into the increase in pebble flux. We are doing it actively right now, and we expect soon. Also, we have our approach is the simplistic one employee per disk. Things can really be very interesting, especially multiplicity can even slow down pebble accretion more due to enhanced eccentricity. So it's really something interesting, and it will be added in future. Also, we did not account for ejection of gas giant planets, especially at the outskirts of the disk due to encounters. And also our approach immediately stopped when the disk is dispersed. Therefore, we did not capture the important aspect of long-time evolution after the disk evolution. So this will really be incorporated, especially when one has fast computing resource available. Thank you for listening.